So this is a question about haloalkanes, but also touches on organic synthesis, as you can see from the multiple steps here. Now, as you're answering this question, you might need to go back and forward a little in the video to remind yourself, or you might want to make a note of that reaction profile before you carry on. Have a go at the different stages, and once you've tried all of it, we'll review the answers. Okay, parts A and B. Part C. Part D. And that brings us to the end of the question, so now we can review the answers. So in the first instance, we are giving the IUPAC name for the compound given. Now, if you have got time, it really can be beneficial to draw it out in full. That way you can identify what the longest carbon chain is. We know that it's 3. So it's propan. I've got an alcohol, so I'm going to name it propanol. I also know that the alcohol has a greater priority than a methyl group or a bromo, so I'm going to number from that end. So it becomes propan-1-ol. Coming off that, I've got a methyl in the 2 position and a bromo in the 3 position, but those prefixes go in alphabetical order. So the only acceptable answer for this question is 3-bromo 2-methyl propan-1-ol. In terms of the nucleophilic substitution mechanism, asking why the haloalkane is attacked by the nucleophile. Well, you can put this into words, and it might be worth adding a little bit more detail as well. But within that haloalkane, in the CBr bond, we have got a more electronegative bromine, which means that we've got a delta negative bromine and a delta positive carbon. And because the carbon is delta positive, the lone pair on the nucleophile is attracted to it and therefore likely to attack it. Moving on to part C, we have got here the infrared spectrum of compound Y. It's showing a significant absorption in the range 1680 to 1750. Now that immediately stands out as a carbonyl. We also know, if we look back at the original reaction pathways, that we're starting with a diol. So it makes sense that from that diol, we are going to make a dioic acid. And so we see this. Methyl propane dioic acid. We move on to part D. Here we've got compound Z with an empirical formula of C3H4NO. I need the compound and I need to suggest the reagent. Now for here, C3 isn't enough carbons. It's going to double to C6, and that gets us thinking about an extension of the carbon chain. Now the way we do that is with nitriles, with KCN, with cyanide ions, forming nitriles. So if I do that, in the presence of an acid, I will end up with my new compound Z.